56 million years ago, Earth ran a fever that outlasted the entire span of human civilization. In a geological instant, global temperatures surged by 5 degrees Celsius, reshaping oceans, ecosystems, and the very chemistry of the atmosphere. Forests spread into the Arctic, mammals underwent explosive diversification, and ancient species vanished as new ones adapted to the heat. When the fever finally broke, the planet was no longer the same. Life itself had been permanently rewired. The late Paleocene world would have felt alien beneath your feet. No ice crowned the poles. Where today's Arctic Ocean freezes solid, cypress swamps stretched endlessly under a sun that never quite set during the summer months. Antarctica wore forests like green fur, temperate rainforest thriving where penguins now huddle against blizzards. The oceans ran hot as bathwater. Surface temperatures in the tropics reached 35 degrees Celsius, hot enough to kill most modern coral reefs within weeks. Even around Antarctica, seawater warmed to 10 degrees, comfortable enough for a quick swim in shorts. Continents are closer together than today's map suggests. North America and Europe touched hands across the high Arctic through intermittent land bridges. South America floated as an island continent, severed from northern landmasses. India continued its slow-motion collision course toward Asia, still thousands of kilometers from the impact that would birth the Himalayas. This was the age of mammals. But mammals were unlike any alive today. No horses thundered across plains. Their ancestors scurried through underbrush, badger-sized and built for hiding. Primates had not yet appeared on northern continents. The largest predators were crocodilians and early carnivorous mammals, no bigger than wolves. Deep beneath the ocean surface, a different world thrived in permanent darkness. The seafloor teemed with benthic foraminifera, microscopic organisms that built intricate shells from calcium carbonate. These tiny architects created some of the ocean's most diverse communities, their shells accumulating in sediment layers that would preserve their stories for 56 million years. The climate had been stable for millions of years. Life had adapted to this greenhouse world, evolved within its warm embrace, and found ecological niches in every available corner. Plants like palms, cycads, and ferns dominated forests, even in high-latitude areas like Wyoming and what would become London. Nothing suggested the coming catastrophe. The deep-sea ecosystem represented one of Earth's most stable biological communities. Benthic foraminifera had weathered ice ages and warming periods for tens of millions of years, their microscopic shells recording the slow pulse of geological time. Their communities stretched across every ocean basin, from the shallow continental shelves to the deepest abyssal plains. Beneath the North Atlantic, geological forces were tearing apart the boundary between Greenland and Europe. Massive volcanic eruptions split the seafloor as the Atlantic Ocean widened, but the volcanism did more than spew lava. It baked. Underground lay vast deposits of organic sediments, ancient coal seams, oil shales, compressed plant matter from previous geological ages. As volcanic heat penetrated these deposits, it cooked them like a planetary pressure cooker. The organic carbon transformed into methane and carbon dioxide, greenhouse gases that erupted from the Earth in quantities that dwarf human understanding. Between 2,000 and 10,000 gigatons of carbon burst into the atmosphere over just a few thousand years. For comparison, humanity has released roughly 500 gigatons since the Industrial Revolution began. The PETM carbon bomb was 20 times larger, compressed into a time frame that, while brief by geological standards, stretched across dozens of human lifetimes. The carbon carried a distinctive signature. It was isotopically light, depleted in the heavier carbon-13 isotope that characterizes atmospheric carbon. This fingerprint would be preserved in every shell, every leaf, every piece of organic matter formed during those critical millennia, creating a global geochemical marker that scientists can read like a neon sign in the rock record. The North Atlantic igneous province represented one of the largest volcanic events in Earth's history. The eruptions didn't occur as single catastrophic blasts, but as sustained volcanic activity that persisted for thousands of years. Each eruption heated more organic deposits, releasing more carbon in a feedback loop that would reshape the planet's atmosphere. The atmosphere's chemistry shifted within centuries. Carbon dioxide concentrations spiked beyond anything Earth had experienced in millions of years. The planet's natural greenhouse effect amplified dramatically, trapping heat that would transform every ecosystem from equator to pole. Methane played a particularly sinister role. While carbon dioxide persists in the atmosphere for centuries, methane is a far more potent greenhouse gas in the short term, roughly 28 times more effective at trapping heat than CO2. The massive methane releases from the baked organic sediments acted like a planetary blowtorch, accelerating the initial warming that would trigger further carbon release. The oceans absorbed massive quantities of this excess carbon dioxide, triggering a chemical crisis that rippled through every drop of seawater on the planet. When carbon dioxide dissolves in water, it forms carbonic acid, lowering the pH and making the ocean more acidic, the same process that makes carbonated drinks taste tangy. But this was no gentle fizz. The acidification happened at a pace that gave marine life no time to adapt. For organisms that built their shells and skeletons from calcium carbonate, the changing chemistry proved catastrophic. Acidic water made it harder to construct shells and could even dissolve existing ones. The deep ocean floor became a graveyard. Benthic foraminifera, those microscopic shell builders that had thrived for millions of years, faced extinction on a scale not seen in 90 million years. Between 30 and 50% of all deep-sea forum species vanished. Their fossil record shows a stark boundary. Below the PETM layer, diverse communities flourished. Above it, only a few disaster-tolerant species survived. The warming water created a second crisis. Hot water holds less dissolved oxygen than cold water. The same reason warm soda goes flat faster than cold. As ocean temperatures spiked, vast regions became hypoxic or completely anoxic, dead zones where complex life simply could not survive. These oxygen-starved waters spread across the deep ocean basins. Fish, crustaceans, and other mobile animals could flee to shallower, more oxygen-rich waters near the surface. But bottom-dwelling organisms had nowhere to go. The seafloor communities that had persisted through multiple ice ages and warming periods finally met their match. The chemistry of calcium carbonate shell formation depends on precise pH levels and carbonate ion concentrations. As the oceans acidified, the saturation horizon, the depth below which calcium carbonate dissolves, moved closer to the surface. Entire regions of the deep ocean became corrosive to the shells that had fallen from surface waters for millions of years. The thermal expansion of warming seawater raised global sea levels significantly, even without major ice sheets to melt. Coastal areas around the world found themselves underwater as the ocean claimed new territory. The warmer water expanded like mercury in a thermometer, pushing sea levels meters higher than pre-PETM levels. Surface waters reached temperatures that would be lethal to most modern marine life. The tropical oceans became bathwater warm zones where few complex organisms could survive the thermal stress. Marine food webs collapsed as plankton communities reorganized around the few species that could tolerate the extreme conditions. On land, mammals faced a world transformed beyond recognition. The supercharged atmosphere created weather patterns more extreme than anything in their evolutionary experience. The hydrological cycle intensified, bringing torrential seasonal rains to some regions, while leaving others parched by prolonged droughts. Plant communities shifted and reorganized as species adapted to the new conditions, or migrated toward more hospitable climates. Subtropical vegetation pushed toward the poles. The Arctic, already warm, became home to plants typically found in modern Florida or the Gulf Coast. For mammals, the heat posed a fundamental physiological challenge. Larger bodies retain heat more efficiently than smaller ones, an advantage in cold climates but a liability when global temperatures spike by 5 degrees. Evolution responded with dramatic speed. The best documented case involves Cephorhippus, an early ancestor of horses. At the beginning of the PETM, these proto-horses weighed about 5.5 kilograms, roughly the size of a small dog. Within 130,000 years, they had shrunk by 30% to just 4 kilograms, about the size of a house cat. This evolutionary dwarfism followed Bergmann's rule in reverse. While animals in colder climates tend to be larger to conserve heat, animals in hotter climates benefit from smaller bodies with higher surface area to volume ratios that shed heat more efficiently. Smaller bodies also required fewer resources, a crucial advantage when high carbon dioxide levels may have reduced the nutritional quality of plants. The shrinking wasn't permanent. As temperatures eventually cooled, Sipherhippus gradually regained its original size, demonstrating evolution's ability to track environmental changes in real time across relatively short geological timescales. Other mammal groups showed similar responses. Body sizes decreased across multiple lineages as natural selection favored individuals better adapted to heat stress. The fossil record from the Bighorn Basin in Wyoming shows this pattern repeated in different mammal families, a coordinated evolutionary response to planetary heating. The high CO2 atmosphere may have fundamentally altered plant nutrition. Elevated carbon dioxide levels can reduce protein content in plant tissues while increasing fiber and defensive compounds. This would have forced herbivorous mammals to process more food to meet their nutritional needs, making smaller, more efficient body sizes even more advantageous. The polar regions underwent the most dramatic metamorphosis. What had been cool temperate forests became subtropical swamps virtually overnight in geological terms. Palm trees and crocodilians appeared in regions that today remain frozen year-round. This transformation turned the Arctic from a barrier into a bridge. For the first time, the ice-free polar regions created viable migration corridors, connecting Asia, North America, and Europe. Mammals that had been isolated on separate continents suddenly found superhighways across the top of the world. 3 major groups of mammals made this transcontinental journey almost simultaneously, appearing in the fossil record of North America and Europe at precisely the same time as the PETM began. First came the primates, the earliest members of our own lineage, small lemur-like creatures that would give rise to all later primate diversity. Artiodactyls followed close behind, the even-toed ungulates that would eventually diversify into deer, camels, pigs, and hippos. Their cloven hooves would reshape terrestrial ecosystems across multiple continents. Perissodactyls completed the trio, odd-toed ungulates, including the ancestors of horses, rhinoceroses, and tapirs. These 3 groups would come to dominate mammalian life across the northern hemisphere, but their global spread began with a single moment when the Arctic ice melted and opened the world to wandering. The migration wasn't just about geography, it was about opportunity. The extreme climate had disrupted established ecosystems, clearing ecological niches and creating new possibilities for evolutionary experimentation. The mammals that successfully crossed the Arctic bridges found a world of open niches waiting to be filled. The Arctic Ocean during the PETM resembled something like the modern Everglades or Louisiana bayous, warm, humid, swampy environments with alligators basking under palm fronds. These conditions persisted year-round, eliminating the seasonal freeze that would normally halt mammalian migration. Fossil evidence from Ellesmere Island in the Canadian Arctic reveals a remarkably diverse ecosystem during the PETM. Alligator fossils appear alongside remains of early primates, giant tortoises, and subtropical plants. This Arctic Eden provided abundant resources for migrating mammals and served as a staging ground for global dispersal. The land bridges themselves shifted with sea level changes and tectonic activity. At times, mammals could walk dryshod from Asia to North America across Beringia. At other times, they island hopped across narrow water gaps using temporary land bridges that appeared and disappeared with changing sea levels. Earth possesses natural mechanisms for removing excess carbon from the atmosphere, but they operate on timescales that make human lifespans seem like brief flickers. The planet's long-term thermostat relies on a process called silicate weathering, where carbon dioxide in the atmosphere dissolves in rainwater to form weak carbonic acid. This acid acid rain, much gentler than the term suggests, slowly dissolves silicate rocks on land. The chemical weathering releases ions, including bicarbonate, which wash into the oceans through rivers and streams. Marine organisms use these dissolved minerals to build their calcium carbonate shells and skeletons. When these organisms die, their shells sink to the seafloor, effectively burying carbon in sediment layers. Over millions of years, this buried carbon becomes limestone, permanently removing it from the active carbon cycle. This process acts as Earth's primary long-term climate stabilizer, but it operates on timescales measured in hundreds of thousands of years. The PETM recovery took between 150,000 and 200,000 years, longer than modern humans have existed as a species. The peak heating lasted only a few thousand years, but the full warming event and subsequent cooling stretched across timescales that encompass the rise and fall of entire civilizations in deep time. During the recovery phase, enhanced weathering rates gradually drew down atmospheric carbon dioxide. The warmer, more acidic rainfall accelerated the dissolution of silicate minerals on land. Rivers carried higher loads of dissolved ions to the oceans, where they were incorporated into marine organisms and eventually buried in seafloor sediments. The process wasn't uniform or steady. Climate feedback loops created periods of rapid cooling, punctuated by temporary warming spikes. Ocean circulation patterns reorganized multiple times as temperature gradients shifted. The deep sea extinction had eliminated many carbonate-producing organisms, temporarily reducing one of the ocean's main carbon removal pathways. When the fever finally broke, Earth had not returned to its previous state. The massive die-offs in the oceans and the evolutionary upheavals on land had permanently reset the trajectory of life on the planet. The world remained warm. The subsequent Eocene epoch was the hottest period of the last 66 million years, but the extreme heat of the PETM had passed. New ecosystems emerged from the chaos. In the oceans, surviving forum species radiated into empty ecological niches, eventually rebuilding deep-sea biodiversity, but with entirely different players. On land, the mammal groups that had successfully migrated during the PET began their explosive diversification into the forms that would dominate Cenozoic ecosystems. Scientists discovered this ancient catastrophe buried in layers of mud on the ocean floor. Deep-sea drilling projects extract long cylinders of sediment that preserve Earth's history in compressed layers, like pages in a book written by geological time. The PETM appears as a distinctive clay layer in these cores, often darker in color than the sediments above and below it. This layer can be found in cores from every ocean basin, creating a global marker horizon that allows scientists to correlate the timing of the event worldwide with extraordinary precision. The smoking gun comes from carbon isotopes. There are two stable forms of carbon: the common, lighter carbon-12, and the rarer, heavier carbon-13. Plants preferentially use the lighter isotope during photosynthesis, which means that carbon from organic sources, like the baked sediments that fueled the PEM, has a distinctive isotopic signature. When thousands of gigatons of this isotopically light carbon flooded the atmosphere, it changed the carbon isotope ratio of the entire planet. This signature shows up in the fossil shells of foraminifera, in organic matter preserved in sediments, and in any other carbon-bearing material that formed during the event. Scientists call this the carbon isotope excursion, a sharp negative spike in the carbon-13 ratio that serves as a global fingerprint for the PETM. The excursion appears in rocks from every continent and every ocean, providing incontrovertible evidence for a planetary-scale carbon release event. The physical fossils complete the picture. The mass extinction of benthic foraminifera creates a clear boundary in the sediment layers. On land, fossilized teeth and bones from places like Wyoming's Bighorn Basin document the shrinking of mammals like Cypherhippus and the sudden appearance of primates, artiodactyls, and perissodactyls. Fossilized pollen and leaves show how plant communities reorganized, with species adapted to cooler climates disappearing from the record, while heat-adapted species expanded their ranges toward the poles. The isotope excursion itself tells a complex story. The initial spike was rapid and dramatic, followed by a gradual recovery that mirrors the slow drawdown of atmospheric carbon through weathering processes. Different materials record slightly different isotope curves, revealing details about how carbon moved between the atmosphere, oceans, and living organisms. Deep sea cores from around the world show the same pattern, a sharp negative carbon isotope excursion coinciding with forum extinctions and changes in sediment chemistry. This global correlation proves the PETM was truly a planetary event, not a regional phenomenon. Modern analytical techniques can measure carbon isotope ratios with incredible precision, allowing scientists to track even subtle changes in the global carbon cycle. These measurements reveal that the PETM carbon release happened in multiple pulses, not as a single massive event, suggesting complex feedback loops between volcanism, sediment heating, and carbon cycling. The PETM stands as perhaps the best ancient analog for modern climate change, with one crucial difference. Today's carbon release is happening at least 10 times faster than the rate that triggered Earth's ancient fever. The organisms of 56 million years ago had thousands of years to adapt to their changing world. Modern ecosystems have decades at most. The rocks remember what happened last time Earth heated by 5 degrees. They remember the mass extinctions, the evolutionary upheavals, the 200,000 years it took for the planet to recover. They remember it all, waiting in ocean sediments and fossil-bearing formations for scientists to read their ancient warning written in stone. In the end, the PETM reveals something both terrifying and oddly reassuring. Earth has survived planetary fever before, but only by fundamentally rewiring the fabric of life itself.